Hello guys, welcome on Tesla Adventures. In this video, today we are going to discuss the motion of the charge in oblique magnetic field. Now, what do I mean by oblique? Oblique means that the direction of projection of the charge, which is the direction of velocity, is at some angle theta with the magnetic field. So you can see in the case that this charge of charge q and mass m is being projected with some velocity v in the direction perpendicular in the direction at an angle of theta with the magnetic field. Now first of all, let us resolve this velocity into two components. The first component is along the magnetic field, and we are denoting it by V parallel, and V parallel will be V cos theta, and the other component V perpendicular will be V sin theta. These are the two components of the velocities. Now for some time let us forget this component and let us ignore this one. We know that if this velocity, if the particle is projected with a velocity v perpendicular in the direction perpendicular to the magnetic field like that, then its motion would be circular motion, and this circle would be in the plane which is perpendicular to the magnetic field. And this plane will be, in this case, will be the YZ plane. So this charge will rotate in YZ plane, and if I draw this diagram in YZ plane, let us draw the view from x-axis. So this is view from x-axis. We are watching it from x-axis. So this would be the y-axis and this would be the z-axis if we are watching from x-axis. And this particle would be initial velocity was v perpendicular in the y direction, magnetic field is in plus x direction, and force will be in z direction like that. So this particle would go like that. This is v perpendicular, so it would go like that. Okay, so this will be the radius of the particle, and the centripetal force would be acting towards the center always like that. And we can also see that the centripetal force in this case will be F magnetic, and magnetic force will be Q V perpendicular into B into sin 90, because you can see that magnetic field is towards x-axis and the perpendicular component of the velocity is towards y-axis, which is always perpendicular to the magnetic field. So we can say that the magnetic field FB will be, magnetic force will be QVB, V perpendicular into B. And if we substitute the value of V perpendicular as V sin theta, then we can say that this magnetic field, magnetic force will be Q V perpendicular, or V perpendicular is V sin theta into B. Now you should also note that this theta is the angle at which the charge was projected with the magnetic field. So this theta is fixed, it is not variable. So this is QVB sin theta, and QVB sin theta will be balancing out MV perpendicular square by R. This is the centrifugal force, and obviously we know that V perpendicular is V sin theta. So cancelling this V perpendicular with V sin theta, so we can say that radius of the trajectory would be MV perpendicular upon QB. So radius of this circle would be MV sin theta by QB. This is the radius. Now you should note a very important thing, that we have ignored this V parallel due to the fact that the magnetic force acting on the charge due to this component of velocity will be 0, because this component of velocity is parallel to the magnetic field. Okay, so this we have ignored in terms of force, but we should not ignore that the fact that this V parallel is not 0, which means this charge will continue to move in the direction of the magnetic field and along with its circular path. So if you will cumulatively draw this path, then it would be like that. It would be a spiral path like that. It would come outside the plane towards you and moving in a circle. So if you will view this helical path from the magnetic field direction, then you will see this circular path only, obviously, because if you can imagine a spring, and if you are viewing a spring from its cross section, then that spring would be like a ring. Okay, so you would be observing a ring if you are viewing from the direction of magnetic field, but in general it would be a helical path, and this motion in the direction of magnetic field is due to the fact that this V parallel is the velocity of the charge in the direction of magnetic field, and this charge will move in the direction of magnetic field due to this component of velocity. Okay, so this is the actual path of this charge in the oblique magnetic field, and you can see that it is a helical path, and this is more precise diagram. Now you can see that this is a quantity, physical quantity, that is called as pitch of the helix. Now you can imagine that when this particle will be rotating in a circle, then also it would be moving in the direction of magnetic field, which we have already discussed, and this motion will be due to the parallel component of velocity, V parallel. So pitch, this is pitch, this quantity is called as pitch. Let me show you. So this is called as pitch. So pitch is the quantity. A pitch is something which is the distance traveled by this charge in the direction of magnetic field in one complete rotation, like that. You can imagine that in one complete rotation this charge has moved a distance in the forward direction. This is called as pitch. So obviously we know that the time period of the motion t is 2 pi m by qb, and this time period of revolution is independent of the velocity, so it is just 2 pi m by qb, and the pitch is the distance traveled by the particle in the direction of magnetic field. And we also know that this distance is being traveled by the particle due to V parallel, so we can say that pitch would be V parallel into t. So pitch will be equal to V parallel, which is V cos theta, into time period, which is 2 pi m by qb. So this is the pitch. P is equal to 2 pi m V cos theta upon qb. This is the pitch of the particle or pitch of the helix. You can also relate the pitch with a screw and nut, and you can imagine that there is threadings in the screw, and that the gap between the two threads of the screw is called as pitch, and that gap is the same distance by which the nut will move in the complete rotation along the axis of the screw. Okay, so this is called as pitch. Now this we also have to note the fact that, as we can see, that there is only the presence of magnetic force, and we know that the work done by magnetic force is always 0. So we can say that the work done by F magnetic is always 0, and therefore the kinetic energy of the particle is constant in this motion also. And we have already seen in the last video that what are the instantaneous coordinates of the particle, when it was rotating in a circle in the perpendicular magnetic field. Now there would be additional coordinate in this case, which would be the coordinate of this x-axis, because x is the same direction of the magnetic field, and we can say that in t time it would travel a distance of v parallel into t in the direction of magnetic field. So the kinetic energy of this motion will remain constant, obviously, and we can also find out the radius of curvature, which I think we have already calculated, but let us find out the radius of curvature in this case also. So radius of curvature is the quantity which is f v square upon a perpendicular. Okay, and v is the net velocity of the particle. So a perpendicular is the force acting on the magnetic force acting on the particle, and we know that the magnetic force acting on this particle is in the direction of z-axis, obviously, because velocity is in the direction of y and x, and magnetic force is in z-axis. So we can say that this magnetic force is perpendicular to the net velocity also, and therefore this magnetic force F magnetic will be Q VB, which is V perpendicular into B, and that is equal to MA perpendicular, and V perpendicular is V sine theta, and this is B, and this is MA perpendicular. So A perpendicular will be equal to Q V B sine theta upon M, and radius of curvature RC is V square by A perpendicular. So RC will be equal to MV by QVB sine theta. This is the radius of curvature of this helix, and radius of helix is a different thing. Radius of helix is the radius of this circle which is seen from the cross section. So if you are watching this helix from the cross section, then you would be watching a circle, and the radius of that circle would be the radius of helix, and radius of curvature of helix is the radius of this curvature of helix. You can imagine that you are pulling a spring, and spring is going like that. So each curve of the spring has some radius of curvature. So that is this radius of curvature of this helix. Now let us discuss another situation in which there is the presence of electric field in the direction of magnetic field also. So in this case, let us discuss this situation also. So this is the electric field. One second. This is the electric field in the direction of magnetic field also, and due to the presence of electric field, what we can say that the magnetic force will be still same. F magnetic will be MVB sine theta, and it would be still in the z-axis, z direction, and obviously this motion would be circular from the cross section, but due to V parallel it would be a helical motion, and the pitch of this helix would be along the direction of electric field and magnetic field. But in the previous case, you can see that there was no force acting on the particle in the x direction. So in the previous case, we can say that the V parallel component of the velocity was constant in the x direction. But in this case, due to the presence of this electric field, the V parallel component, which was initially along the x direction, will be variable, and obviously there would be an additional acceleration on the particle A in the x direction, which would be equal to QE by M. So particle would be accelerated in this direction also, which means that this pitch will not be constant, and this pitch would be increasing, and this pitch is increasing due to the fact that particle is getting accelerated in the x direction. Okay, radius of this helix will remain same, r will remain same, r will be mv sine theta upon qb. I am talking about radius and not the radius of curvature, and the component of the electric field, or we can say the component of electric force, will be along the magnetic field direction, and therefore at any time t, the distance traveled by the particle in the direction of magnetic field is x, and this will be equal to ut plus half at square, and u is equal to v parallel and t is time, and plus half a is q e by m, and t square is the time. So this is the x component of the particle at any time t, which was initially only this one, because initially this part was 0 and initially x component was only this one, but now x component is this, and pitch will be the time dependent quantity, because pitch is variable and will be the distance traveled by the particle in one complete rotation in the direction of magnetic field. Now we know that the direction of magnetic field in this case is x-axis, and the acceleration of the particle in x-axis is q e by m, and the distance traveled by the particle at any time t is s, and s will be equal to this is ux, which is u cos theta into t, and plus half a, which is q e by m into t square. This is the distance traveled by the particle in the direction of the magnetic field at any time t. So if we calculate the distance traveled by this particle in one complete time, one complete revolution, then we can say that the distance traveled in 0 to t, then we can substitute the value of 0 to t, and this is pitch 1, and the distance traveled in t to 2t will be pitch 2, and the distance traveled in 2t to 3t will be p3, and so on. So the value of pitch will depend on the fact that which pitch we are calculating. So the pitch at the nth pitch would be equal to the distance traveled in the time n minus 1 t to nt. So to calculate this nth pitch, we can do that Pn is equal to s, distance traveled in nt time, minus distance traveled in n minus 1 t time. Or we can integrate the v parallel at any time t, and we can substitute the limit of the time. So this is the method to calculate the pitch. We further talk about the kinetic energy, then kinetic energy will not be constant. In fact, the work done by electric force will be equal to change in kinetic energy, and obviously we know that electric force will be changing the x component of velocity only. So let us suppose that work done by electric field is W by electric field is equal to electric force into displacement of the particle in the direction of magnetic field, which is x coordinate of the particle at any time t, where x coordinate you can find out by u cos theta into t, and plus half a is q e by m into t square. This is the x coordinate at any time t, and this work done by the particle q e into x will be equal to change in kinetic energy. So change in kinetic energy obviously will be only due to the change in the x component of the velocity. So we can say that it would be Vx square minus Ux square. Ux was initially equal to u cos theta. So Qex will be equal to half m Vx square minus u square cos square theta. This would be the energy equation relating the work done by electric field and the change in the kinetic energy. You can see that I have not taken the v perpendicular in the equation of kinetic energy due to the fact that finally the kinetic energy due to v perpendicular and initially the kinetic energy due to v perpendicular will cancel out each other. So I have not taken that. So this is the final energy equation. And if this, obviously, if this, let us use this diagram. Now, if this electric field will be in the opposite direction of the magnetic field, like that, then obviously the pitch will be decreasing and this acceleration will be the retardation. Particle will go retarding in the direction of magnetic field and it will stop eventually at some point of time and then it will turn back. And the maximum x coordinate of the particle, x max, will be the coordinate where it would stop and return back in the helical path only. So this maximum x coordinate of the particle will be QE, which is the work done against electric field, which is QE into x max, and that is equal to half m Vx square. So you can see that the maximum x coordinate can be calculated by this formula, that half m Vx square upon QE. Now I'll explain you again how I have calculated this thing. You can see that the electric force is acting in the x direction and in fact in the minus x direction. And this electric force will only change the V parallel. V parallel was initially u cos theta. So what we can substitute at the place of Vx, so we can say that Vx, or I can write it down as ux to be more accurate. It is ux, initial velocity in x-axis, and initial velocity in x-axis was u cos theta. So x max, so what we are saying, that this particle is losing its kinetic energy due to V parallel against the work done by the electric field, and therefore the work done by the electric field or work done against the electric field will be equal to the change in the kinetic energy due to V parallel only, because we know that V perpendicular is not getting changed because electric force is acting in the x direction and V perpendicular is acting in the y direction. So V perpendicular is as it is, and when this particle will stop moving in the direction of x direction and when it will return back, then at that point x coordinate would be maximum, and at that point this particle will lose all its kinetic energy due to x component in work done against the electric field. So what we can substitute that x max is equal to half m by QE, and ux is u cos theta or v cos theta initially. So this is the value of x max. Okay, this is the maximum x coordinate when this particle, where this particle will reach, and thereafter it would turn back and it would move in the reverse direction in the helical path. Okay, so this was the analysis of the motion of the particle when it is projected in the oblique magnetic field, and also when the electric field is also present in the direction of magnetic field. So in the next video I would be bringing some best concept illustration problems which are based on the motion of this charged particle in the magnetic field. Thank you.